This is a SolOhm update for February 15th, 2016. I've been really busy in the last couple of weeks. I got the first rev of the hardware done, and I'll go ahead and show you what's going on there. So here's the block diagram. This multimeter is designed to attach to a single panel or a string, where a single panel puts out about maybe 40 volts at the power point. And the multimeter is designed to sit between them. These connections here are on MC4 connectors. So it sits between the panel or string and the inverter. So here's the block diagram here. I'll go over a few things here. It's designed to read from 0 to 1500 volts DC and up to 0 to 40 amps. So it's quite a flexible device. It auto scales on the voltage, the voltmeter, as well as on the ammeter, and it's going to be calibratable, and it's made with somewhat standard parts. It's also designed for wide temperature swings of -20 to +60 degrees C. Let's go over some of the blocks here. Originally, I was going to parasitically charge a LiPo battery off of the high voltage circuit. That proved to be quite problematic when I was considering doing 1500 volt strings. So instead, I opted to put a small PV panel and a transparent lid on the box. I'll show you that in just a minute. So it doesn't parasitically charge off of that. It gets its power off of a onboard PV panel. It's got a battery charger. It runs a single 1S LiPo battery. I've opted to get a 5,000 milliamp hour LiPo battery. It's got a 3.3 voltage regulator. It's got an onboard temperature sensor. It needs to have calibrated readings across the temperature range, so it needs to have a lookup table for calibration data, so it has an onboard temperature sensor. It has an SD card for logging data. It has a real-time clock. It uses the LiPo battery as a battery backup. It needs that for data logging as well. The CPU I've decided upon right now is ESP8266 part. It's a Wi-Fi FCC approved module that is a 32-bit processor. It has a tremendous amount of software support. Then I have a scaling thing to sense the voltage input and a current scaler to take this the value across this shunt resistor up to the ADC. The current design is evaluating two ADCs. One of them is an LTC 2348. It's 18-bit ADD at 200 kilohertz. That's really overkill. It's a very expensive part, but it's a super part. I have that laid down on the board. I'm also evaluating a Maxim 11060 part. That is a simultaneous sampling. Hold on, let me turn off something down here. That's a simultaneously sampled 4-channel differential voltage, 0 to about 2.2 volts. So I have let's go over some schematics. Sorry about the resolution on this. I scaled down my screen, so it kind of looks like crap over here as well. But basically, I have a MOSFET array that switches in different resistors. And I struggled a lot with this circuit because I wanted to have high input impedance. That lowers the power consumption on some of these resistors because at 1500 volts, they're going to consume a lot of power. By making them large, that ended up putting a 3 dB pole frequency for the ADD really low. So the input capacitance on this particular circuit was a little bit of a challenge. I want the frequency bandwidth on the A to D to be right around 3 kilohertz. That'll enable the end user to actually do analysis of the inverter's MPPT algorithm and sample data to do further analysis beyond just straight sampling with averaging. So I have a 2-pole solid key circuit to do a pre-filter in the analog domain before it goes into the digital. And I have a little gain stage here. The LTC part, it wants its full scale rating is up to 4 volts, but the maximum part only wants 2.1. So I have a scale factor in here to kick the voltage up by a factor of 2. There's 6 voltage scales here. There's 0 to 2 volts, so you can look at very small voltages, 0 to 60, 0 to 120, 0 to 350, 0 to 625, 0 to 1550. These voltage ranges were chosen for various string configurations. I have a similar type of arrangement over here. I have a programmable gain amplifier for the current. I'm using a 0.5 milliohm cent resistor, and it's a fairly large part. I think I got a 3 watt part, so I can sense up to about 40 amps of current. Over here, the current ranges on it are 0 to 20, no, 0 to 2, 0 to 10, and 0 to 20, and 0 to 40. And so this circuit here has a pretty high gain on it of about, one of the gains is almost 200, which I'm going to have to evaluate the noise performance on this to figure out if this is a viable way of doing this. On the power consumption, the power stage, I take the PV panel in. I've chosen a relatively inexpensive part. There's a LiPo battery charger. It's from Microchip. It'll take in 7 volts. The VOC on the panel is 6 volts right now, so this is going to work fine. And then I have a 3.3 volt regulator. It's a TLV 702 part, and that's going to give out I can't remember why I chose that part, but anyway, it's what's on the board currently. On the CPU side, it has, like I said, the 8266 part. I opted for the ESP12E module. This is a part that has a 4 megabit flash part embedded on it. It's also FCC approved. The 1 megabyte is used for coding, and 3 megabytes are used for a flash file system. So it does have the capability of storing data file inside the module. I have an I/O expander here. Here's the real-time clock. This is an LM75. It's a temperature sensor that's on board. And then here's the SD card over here. This is programmable over serial initially. We'll go into what the OTA is here in a minute. I have 2 connectors down here to run the external I2C and external SPI connector. This is capable of running a display as well. So if I wanted to get like a color OLED display, I could run it straight off of this external SPI connector. On the ADC, like I said, I had I'm evaluating 2 ADCs right now. The LTC 2348 is an 18-bit A to D at 200 kilohertz, and the max part is 1160, and the 1140 is a 24-bit equivalent. They both sample up to 16 kilohertz. Now, the last thing is this first version is not going to incorporate a temperature sensing on it. To really critically evaluate panel performance, you want to fully instrument those, which includes a paranometer as well as RTDs mounted on the back side of the panel. I've not included that in this design. I'm a little bit up against a time frame crunch right now, so I provisioned for it and I know what parts I'm going to use. That part's going to be a LTC2983, which is a super temperature sensor. And these in order for this to run at the panel level or the string level, it's possible that the negative side of my input string is operating as the circuit's floating ground. So I need to have a like a 2500 volt isolation barrier for external connections out to the external RTDs. So all this stuff is provisioned for in the design. It's just not implemented in this revision. Okay, so I'll go ahead and click on my other camera here. So here's the enclosure I've chosen. It's a Bud Industries plastic enclosure. It's rated IP67. It's got a clear acrylic lid on it. So four screws to hold it down. It's also got these mounting tabs so it can be mounted without really any kind of brackets or anything. Like I said before, it's powered off a PV panel. So I have this 2 watt 6 volt VOC at about 350 milliamps eye short circuit. So this thing is going to put out enough power. I did some external testing. I actually put this out in the sun. I pointed it directly away from the sun, and I get out about 5.5 volts at 50 milliamps. That's usable. So it doesn't really need to be pointed in the sun, so it can be mounted on the backside of a panel in the shade. This PV panel fits exactly right in the inside of this clear plastic enclosure, and I'll just hot glue it in there or something like that. This fits on like this. So the circuit board fits in here. Underneath the circuit board is going to be the LiPo battery. I got this 5,000 milliampere 1S LiPo battery from Hobby King. It's going to sit underneath the circuit board, and the circuit board's going to sit on top and kind of clamp it down in there. There's no through-hole parts on here, so we're not going to have puncture potential to go into the LiPo battery from there. High voltage sides down here, all the digital circuitry is up on top. This radio antenna is dangling off the edge of the circuit board. This PV panel has a little bit of play in it, so up here on the top, the PV panel is not going to obscure the RF from coming out of the lid. I'm using these solder lugs that are going to be held down on the board in this location here. And these cable glands are going to come through the side, and they'll be at the exact height to run the cable right into these lugs without any kind of bending action. These lugs are rated at, let me see, they're rated up to 20 amps at 2,000 volts. Getting a 40 amp connector, I have to find one that's UL listed, and I'll have to rev this area of the board to accommodate that. But right now this guy is going to accommodate up to I think it does 10 gauge wire. This is 12 gauge solar wire. You can see that the insulation's kind of stout, so it's going to fit right through here. So this over here is the couple of development boards I bought. This is that Node MCU board. Originally this came with a Lua interpreter, but I ended up putting over a flasher with the Arduino environment. This is the expressive ESP8266 module, the ESP12E. And so I've been doing some development using this. I also bought this thing from SparkFun called the ESP8266. This thing actually has the same charge circuit on it as well as the part. So I can use this to do some development as well. Okay, the ESP8266 has a tremendous amount of support from the Arduino development environment. It's actually a recognized processor that works right within the Arduino development environment. So you end up cloning this GitHub repository into the right place, and then you just basically run the Arduino development environment. And it has a bunch of example code here for 8266 examples of how to run various types of things. So what I did is I took their OTA client, which is called, OTA stands for over-the-air update. This particular part, like I said, has 1 megabit of flash available for code. Actually, that's 1 megabyte of code space. The OTA mechanism functions in a dual bank kind of operation, so you end up embedding some OTA code into your application, and at any point you can jump to that OTA and program the other component, the other side of the other half of the flash, and then when the microprocessor comes out of reset, it runs either one bank or the other bank, so to speak. So today I worked on this, and I got I followed the instructions down here to get this thing running. I fired up my Node MCU board that I got from Amazon, and I started playing with this today. And so I have this running. I took their example and I added a few features to it. So this is like the base template to actually do OTA. It follows the Arduino philosophy, where you have a setup routine and then you have a loop routine down here. Okay, so I can show you that over here. I was able to get all this running over the serial port. So you come over here and you pick your board, you pick your serial port, and then you hit compile and it runs. And I did a lot of development in this environment and got it all functioning. But at some point, well, I'll just show you over here. I have it functioning over here. I'll go ahead and reboot the board now. You can see it down in this bottom left corner window. Let me clear this thing here. If I can figure out how to do that. Hold on. All right, so I just hit the reset switch. So that's about how long it takes to get associated with the access point. It's about 2 or 3 seconds. There's a unique ID in the chip. So what this is currently doing is this sketch grabs that ID out, and what you're seeing in this window is the console output coming out of the serial port. It's a JSON document that's encoded, just giving out 2 keys, the node ID and the uptime. And then I ended up writing over in this window, I wrote that in addition to printing it on the serial port, I also send it over to UDP port. So I wrote a little UDP listen program that listens on this UDP port. And what this is doing is just basically broadcasting out the CPU uptime every second. And so using UDP packets, we can have multiple listeners connected at the same time, consuming the data as they desire. Okay, so I have 2 UDP listeners over here running, and they're actually basically hooking onto the stream that this particular radio is putting out. So I checked all that code into the GitHub repository over at SolOhm. So that URL is github.com/SolOhm. And I created a Multimeter repository over here. So here's the code that's over here. This is the INO file that you saw me editing over here. You could just take this directly and put it right into your Arduino and run it. The last thing I worked on today was the Arduino environment. When you hit compile, it's not very it doesn't really take advantage of the of Make's ability to look for new files. So it basically recompiles your source code from scratch every time. This is really time consuming, and it's kind of a pain in the ass. So I'm not really used to well, I don't actually like to type in the Arduino environment. I get things running to a point and then I figure out a make file. So the last thing I did this afternoon was I have this make file created. I got it from this repository here. This guy came up with a make ESP for Arduino. I followed his instructions and kind of tweaked his make file a little bit. So over here I can show you, here's that INO file. This directory here that I'm in is a clone of the GitHub repository. So here's my INO file. It's the same one you've seen before. And if I hit make, well, let me just touch the, I'll show you how fast make works. Okay, so there it remade the file, and if I want to upload it, I just do make OTA. And what it's doing is it's uploading it over the airwaves over to the board. And then down here you can see a progress screen. I'll do that, I'll redo that in a minute. There, it just got rebooted. And it's going to associate, and then these things are going to start eavesdropping on the UDP packets again. So you can see this process for doing development is really quite fast. You basically edit the INO file, and you can change something like here. Like I'll change this to test here. And then you make it, and then you make OTA. And it's going to upload it over here. You can see it uploading down at the bottom left. And then it does a watchdog timeout. Then it reboots. It gets reassociated to the access point, and it starts again. You can see that this node ID changed. I've got this word test right here again. So that's where we are right now. I sent the board out on Friday afternoon. I've ordered all the parts for the first prototype run. I had I was using a board house, and I'm not going to say where it is, but I had problems with this board house in the past, so I decided to go over to a board house in Oregon, which is called, I don't know what the heck's that called, Express PCB. And they're making 2 of my boards right now. They'll be here on Wednesday morning. My parts are going to arrive tomorrow. And so I had today and I have tomorrow to kind of get some software running. So I have my development set up, finalized now. I'm going to write some exercising code, and I'll put it on a repository when I get that done. Things like, read from the ADD, read from the real-time clock, read from the temperature sensor, that type of thing. I'm going to take this basic OTA Arduino file and actually create a bunch of baby step code that I call it. And then I'll start writing the application. I can get all that kind of done tomorrow. And then when the hardware shows up, what I'll do is I'll start building out various portions of the circuit and verifying its operation as we go. So I'm very excited about this. I'd like to get a major portion of this done this week. I basically put off everything else for all my other customers and a lot of personal things for the last couple of weeks to get this first rev done. I'm very excited about it, as well as CFE is got a portion of their test facility down in Albuquerque earmarked to do some beta testing for this, and they're ready for it, and that's a good thing. So I'm going to sign off for now. Thanks for watching, and that's the SolOhm update for today, February 16, 2016.